Okay, so as I mentioned, the plan for today is to introduce the idea of triple integrals, and in Wednesday's class to talk about the analog of polar coordinates and double integrals, namely cylindrical and spherical coordinates in triple integrals, and then leaving as our supplements surface area and change of variables, a couple of topics that are important, but maybe of less central importance than 15.6 through 15.8. Okay, so triple integrals. One super important note that I think we need to be careful of is noting the difference between a double and a triple integral. So a double integral integrates a surface over a 2D domain. So here I have an example of a two-dimensional domain in the XY plane. This kind of what looks like a quarter circle here in the XY plane. This is the domain D. And then this, it looks like maybe 1/8 of a sphere is f of x, y. The surface that we're integrating, the integrand, is represented by this surface, this kind of teal color here, and the region R, or I call it a D over here, or R. The region over which we're integrating is this like maybe quarter circle in the XY plane. And we think of making Riemann boxes, the height of which is related to the surface, related to that teal surface up here. Now, a triple integral, what do we mean by a triple integral? Well, we're looking at something like this. We're looking at a triple integral of a function of 3 variables. So double integrals integrate integrands that are functions of 2 variables. Maybe we don't see explicitly both variables, but kind of implicitly a function of 2 variables. Triple integrals integrate functions, their integrands are functions of 3 variables. That's why we have a triple integral. Now, it can be kind of confusing, and I know I even have to be careful to kind of keep this straight when we're drawing integrals, when we're making some kind of geometric representation to help us figure out the problem. You can kind of see, I stole these pictures from a different book, but these aren't from Stewart, these are from the Larson book. But I think they do a really good job. You can see how similar these two pictures look between a double and a triple integral, but note that they're representing very different things. A triple integral integrates a function of 3 variables over, and this is the important part, a 3D domain. So a double integral, the kind of whole integral, the region of integration and the surface and the volume between all of that represents a volume. So the integral as a whole represents a volume, whereas in a triple integral, the domain itself represents a volume. The geometric interpretation of the whole integral, we've stepped up a dimension, is a 4D solid, which of course we can't really reasonably graph. So typically what we do is we graph for a triple integral the 3D domain of integration. So we, would graph something analogous to this in a double integral. So that's what we're seeing, for instance, here. We're seeing the volume of integration. We're seeing the domain, the inputs being graphed. And we're not making any attempt to graph the integrand, the function, the kind of hypersurface or whatever you want to call it. And when we imagine breaking up this domain, instead of breaking up the domain into 2-dimensional rectangles, we break it up into 3-dimensional, essentially cubes or cuboids of some sort. So we break the domain into three-dimensional cubes, and inside of each cube, that cube represents a volume, a certain amount of the domain, say a dv, a little increment of volume. And my function f, often we can kind of think of f as maybe a temperature at each point. I can sample the temperature somewhere in say, for instance, this cube. I sample the temperature somewhere in there that gives me a temperature, and I just kind of assign that temperature to that entire cube. So I have a little increment of volume that gets assigned that temperature over that whole increment of volume. And a different increment of volume would likely get a different temperature assigned to it. And then I kind of add up all of these, in a sense, like temperature times volume things. So again, the important thing to note is whether we're doing a double integral or a triple integral, we tend to, in both cases, draw a three-dimensional geometric structure, but they mean very different things. The double integral, that three-dimensional geometric structure, kind of represents the whole integral. It represents the domain in, say, the xy plane, as well as that whole solid under the surface. Whereas in a triple integral, when we draw a 3D structure, we're typically, well, we are just drawing the domain, and we typically draw the domain to help us figure out what our bounds of integration are going to be. Okay, so okay, yeah, question in chat. So we're not given the diagrams on the exams. Do you have any tips how we can remember the process for solving the problems as far as area, volume, etc.? So one thing is to note, I think this might address what you're asking. If I'm not answering the question that you're asking, please let me know. But one thing that I note is that, well, dA is a little increment of area. And if I took f in both cases just to be everywhere one, the number one, then I'm either looking at double integral over r of 1 dA. In other words, I'm adding up a whole bunch of little increments of area. This is going to be an area. Whereas in a triple integral over some region, for whatever reason, in triple integrals, we tend to call the region E, or I think in some books I've seen it called like script W. I'm not really sure why they tend to call it R or D in 2 dimensions and like E or W in 3, but integrating E dV, we're adding up a bunch of little increments of volume. So essentially what we're doing is we're assigning a quote temperature of 1 to each of these cubes. And then we end up just adding up the volume of each of these little cubes that we can see kind of fill in this three-dimensional region. So this is a volume. So if I take the double integral of 1 dA, that gives me an area because I'm adding up an increment of area to get a total area. And if I take the triple integral of 1 dV, I'm adding up increments of volume to give me a total volume. So I don't know if that answers your question or not. Of course, the kind of cop-out answer to your question is, well, as you work through the homework and work through example problems and so on, you do kind of get a feel for what's going on. So, the more problems that you do and that you work through, the better of a feel you get for some of these little nuances. But hopefully that gives you a little bit more to go on. And again, if I didn't actually address the question you were asking, if you either want to type it in chat or unmute yourself and ask, I'd be happy to answer further, but maybe as we go on, that might clarify some things as well.
Okay, so
but okay, so
answering my question.
Yeah, so the big thing that I want to get out of the way first is that in both double and triple integrals, we tend to draw a three-dimensional geometric shape, but we just have to be very careful that they mean very different things. In double integrals, it's kind of the entire integral, the domain and the surface and the volume in between that we're interested in. Whereas in triple integrals, when we're drawing a 3D shape, we're thinking of that as just the domain. And then kind of at each point in 3 dimensions, we can kind of imagine that we have a temperature reading or something that we're adding up in each of these little cubes. All right, so let's look at some examples. So we'll start with example 0 here. I called it example 0, in part because I had already numbered some other examples, but also because it's a pretty straightforward example. So we want to evaluate this triple integral. So we note that z goes from 1 to 4, y goes from 0 to 3, and x goes from 2 to 6. And there is absolutely no dependence of any of these on any of the others, of these boundaries of the regions. So it's not something like y goes from 0 to x minus z or something like that, where that upper bound on y might depend on what numbers I have chosen for x and z. I can choose z any way that I want, independent of x and y. I can choose y any way I want between 0 and 3, independent of x and z, and then the same for x. So this is kind of the analog of a rectangular region in double integrals. This is kind of a cuboid type region. And so I know what x ranges between 2 and 6, independent of y and z. Y ranges between 0 and 3, again, independent of x and z. And z ranges between 1 and 4, again, independent of x and y. So at height 1 on the z-axis, I have a line above the x-axis going from x equals 2 to x equals 6, and same at height z equals 4. So this is kind of the side of the box that aligns with the xz plane. Note that y goes down to 0, so that side of the box really is sitting on the xz plane. And then we go in the y direction 3 units. And again, we just come out from every point in this this little rectangular segment here in the xz plane. We come out to the right 3 units because, again, y is independent of x or z. So, and I know there's a lot of lines on the screen, but we can kind of see, I think, that this is our little cuboid of integration here. And very importantly, this is E, the domain of integration. This has nothing to do with the integrand. We could have all kinds of different things in the integrand, and we would still get the same domain if our triple integral had these same bounds. Now, it's not strictly necessary to do this for this problem, but I think it is helpful, though. We might also notice that our integrand can be written as the product of 3 functions, x squared times, remember our exponent rule is e to the y plus 3z is e to the y times e to the 3z. Well, this is just the product of a function of x times a function of y times a function of z. And none of my bounds of integration depend on any other variable. They're all independent. So if I want to take a shortcut, I can actually pull all of these apart. Integral 1 to 4, that goes with x. So that's my x squared dx times integral 0 to 3. That's my y integral. So that's e to the y dy. And then integral 2 to 6. That's my z integral. So that's e to the 3z dz. Right? I could have gone through this, super carefully and pulled out x squared times e to the y out of the inner z integral and got an integral 2 to 6 e to the 3z dz. That would be a constant. That could come all the way out in front of both of the y and x integrals because it's just a constant at that point once it's a definite integral just in z. And then I could do something similar, pull the x squared out of the dy integral, and then integral 0 to 3 e to the y dy would be a constant, so it could come out of the x integral. So I could go through it step by step if I really wanted to, but I think we can kind of see that it's going to work out that way without going through all of that extra detail. And what is this? Well, this is 1/3 x cubed from 1 to 4. E to the y from 0 to 3. And this is 1/3 e to the 3z from 2 to 6. Or it looks like I have what, a 1/9. So that takes care of these constants. X cubed from 1 to 4 gives me 64 minus 1. E to the y from 0 to 3 gives me e cubed minus 1. E to the 3z from 2 to 6 gives me e to the 18 minus e to the 6. And we might be able to simplify this a little bit. Actually, we can't. 64 minus 1 is 63. And 9 times 7 is 63. So that simplifies pretty nicely. I don't think we can really do much with all of these exponentials, though. But we end up with 7 times these two exponential bits here. Now, importantly, the reason we were able to break these integrals up like this is that we had both the ability to break the integrand up into the product of function of x, function of y, function of z, and also we didn't have a dependence in the bounds of integration. If we had, say a sine of x plus y or something like that, probably wouldn't have worked as nicely if that was, say, in the integrand, or if we had a region that wasn't a nice little box, but where there was some coupling between at least two of the variables, then it wouldn't have worked as nicely either. But we always want to be on the lookout for symmetry. And in particular, when we draw out a domain and we see that we have a nice rectangular bit or a nice kind of symmetric bit to the domain, that just kind of catches our eye and we say, hey, we might be able to leverage that here. If our integrand cooperates, then that can make our life a little bit simpler. Any questions on that one? Okay. And so again, just to remember, we integrated over a domain that's a volume, we integrated this function. So if I said, what is this number, 7 times this at the end here, it represents some kind of like 4-dimensional hypervolume of some sort. Not something that is very easy to draw or really even to imagine. But we note that the process, the kind of algebraic process, felt very similar to double integrals. Right? Sometimes we want to lean more heavily on the geometric side of things. Sometimes we want to lean more heavily on the algebraic side of things. Okay, let's look at the next example. Let's evaluate this triple integral of e to the x times y plus 2z, where e is the region where x is between 0 and 2, y is between 0 and x, and z is between 0 and x plus y. And I gave a little hint down here so that we don't have to do the bunch of integration by parts at one point in this problem. Okay, so let's again try to draw out our region. Now x goes between 0 and 2, y between 0 and x. Those are pretty straightforward. Let's start with the most complicated bit. Z going between 0 and x plus y. Well, z equals 0 is just the xy plane. Z equals x plus y. Well, so if I think of z equals x plus y, when y is 0, when I'm in the xz plane, what does that projection look like? Looks like z equals x. And I know that z is positive and x is positive, so I'll just draw this piece of z equals x. This is the 45-degree line in the xz plane, in the positive quadrant of the xz plane. When x is 0, when I'm in the yz plane, I get something similar, just z equals y. That's this 45-degree line in the yz plane. So I have a plane that is coming down, it's going through the origin, and it's kind of slicing the origin at like 45 degrees. So the chunk of this plane in the first octant here, if I kind of cut it off at some point, kind of looks like a triangle like this, but this triangle is at a 45 degrees going kind of into the screen. So this line at the top of the triangle is kind of maybe above, say, this line here in the XY plane. And then, of course, this point here is at the origin. So that's our plane z equals x plus y. Z goes between 0 and that plane. Y goes between 0 and x, so y equals 0 is the x-axis. And y equals x is the 45-degree line in the xy plane. So this is y equals x and y equals 0. And then lastly, x goes between 0 and 2. So what I have is, let me draw this blue y equals x kind of projected up into the plane. So my region of integration, my volume of integration, is something that looks from this perspective like, it looks like a pyramid where we're looking through the bottom of the pyramid towards the tip. So if you think of a pyramid has like a rectangular base and a point at the top, if you put the point at the origin, lay one of its 4 sides on the xz plane and the other of its 4 sides, or another of its 4 sides on the xy plane, that's what we're kind of looking at here. It's so it's a pyramid like this. But tilted kind of onto its side. So that's what we're looking at. We have the point at the origin, and then we're looking from this perspective through the base. So I know there's a lot of lines drawn on here and everything, trying to make it clear what's going on. Okay, so what do I want my bounds of integration to be? Well, nicely enough, this doesn't require a whole heck of a lot of thought. We just integrate what do you want? Well, z depends on x and y depends on x, and x doesn't depend on anything. So let's put x on the outside. We'll put y as the middle integral. Y goes from 0 to x. And then z as the inner integral. I think all my dependencies are handled here, right? I wouldn't want to put, say, z as the middle integral, because then I have a y that is outside of the y integral side. I'm kind of stuck doing it this way unless I wanted to change the order of integration for some reason. If I had an integrand that looked like it was hard to integrate, but I don't think that's going to be a problem with this integrand.
So when you're choosing the order of the integration for the problem, does it just depend, I guess, on what the problem is, to choose whether you want like Z or X or Y to go first, second, or last?
So sorry, could you repeat the first half of that? I had my volume down kind of low.
No, that's okay. Does it depend on the problem, for like which one of the variables you choose to go first, like X, Y, or Z?
Yeah, absolutely. So it depends on uh well, so some problems like this one, it doesn't matter. Because we see that we literally could pull them all apart and put them back
Yeah,
together or
yeah,
order we want it. But quite often, either the volume of integration, this region E, and or the integrand is gonna, at the very least, make your life a whole lot easier, maybe going one direction versus the other, one order versus a different order. And we're actually going to see in the next example here, if we don't change the order of integration, if we kind of leave it in this kind of order that's given to us, well, we end up having to integrate sine of y squared, and we don't really know how to do that.
yeah. Okay.
But I do know how to integrate y times sine of y squared. I can do a substitution there. So that actually kind of saves the day a bit. That extra factor of y, if we can rearrange this volume of integration in a different way to get a factor of y to pop out before we have to do the y integral, that matches a lot nicer with this integrand. Or sometimes the region of integration, like here, for instance, the way that things are set up, it's much easier to integrate z first and then y and then x. If we say really wanted to integrate, I don't know, z is the outer integral and x is the middle and y is the inner. In theory, we could do that. It's not a problem, but it would be a lot of work for us to kind of look at the geometric region and reset everything up so that all of our bounds are correct. But yeah, that's a good question. Is quite often, yeah, either the region and or the integrand, rewards us for picking a specific order. It makes our lives a lot easier. Yep.
Okay, got it. Thank you.
Mhm. Okay, but here we're given a kind of naturally a specific order, and the integrand doesn't really suggest that we should go with any different order, so we'll just stick with that. I note that this e to the x can actually pop all the way out here. Just gives me fewer things to keep track of. And then I'm integrating y plus 2z dz, so that's going to be yz plus z squared from z equals 0 to x plus y dy dx. Okay, and then I have y times z x plus y plus x plus y squared. And then minus when z is 0, that zeroes everything out, dy dx. And this gives me, let me actually just come over to the side here and do this. I get xy plus y squared plus x squared plus 2xy plus y squared. And if we collect like terms, we get 2y squared plus x squared plus 3xy. All right, and now we integrate this, we get 2/3 y cubed. We're integrating with respect to y. So I don't know, with me, if I'm going quickly through these, it's kind of tempting to make this like, 1/3 x cubed or something like that. But remember, this is just with respect to y. So just plus y x squared plus 3/2 x y squared, y going from 0 to x, and integrating that dx. And of course, everything has a factor of y in it, so the y equals 0 is going to zero out. And when we swap in a y equals x, I get 2/3 x cubed plus x cubed plus 3/2 x cubed dx. Need a little more room here. And this gives me x cubed e to the x dx with a constant of 2/3 plus 1 plus 3/2, or that's what, 4/6 plus 6/6 plus 9/6, or 19/6 if I did all my arithmetic right. And then using this hint up here. Did I do this? I didn't actually calculate this one all the way out, but at this point, I'm just going to say dot, dot, dot. Just evaluating this function, e to the x times x cubed minus 3x squared plus 6x minus 6, between x equals 0 and x equals 2, multiplying by 19/6, and that gives us the answer. So slightly more complicated region of integration or volume of integration, but it was set up pretty nicely for us. We didn't really have to do a whole lot of work. We just had to kind of read this off and set up our integral. Now let's look at this example. Here I also have a region that's set up, pretty nicely. I do see that y depends on x, or the y bounds depend on x. So I want my y integral to be inside of the x integral, at least kind of naturally speaking, and x and z don't have any dependencies on the other variables. X just goes between 0 and root pi over 2, and z between 1 and 3. So I guess I could integrate, x on the outside, then z, then y, or z on the outside, then x, then y. As long as the y integral is inside of the x integral, I'm fine as far as the bounds go. But I do have a little bit of a challenge here in that this integrand isn't super nice. I'm not sure why my integral down here is not as big as it is up there, but my integrand is not super nice. Sine of y squared. If I want my y integral inside of the x integral, then I'm going to have to integrate sine of y squared dy. The z isn't going to help me out. If I put the z integral inside or outside of the y integral, it doesn't really matter. I don't see any dependence on z in my integrand or in any of my other bounds of integration. That z bit is just completely independent of everything else. It's just going to give us a factor of 2. So how do I resolve this problem? I don't know how to integrate sine of y squared, and if I set things up with the y integral on the inside, I have to integrate sine of y squared dy with no extra help with, a factor for substitution or anything like that. Well, maybe what I could do is change my order of integration. Maybe I could try to put my x integral inside of the y integral. I do know that x and y are related. Maybe if I try putting my x integral inside of the y integral, maybe somehow I'll magically get out a factor of y that can help me integrate this integrand here. Okay. This isn't something we're doing to make this theoretically possible. I mean, in theory, it doesn't really matter which way we, which order we integrate in, but practically it makes a big difference, right? Whether or not I can write down an antiderivative in a nice closed form expression, if I can do that, it makes my life a whole lot easier. Okay, so my goal is to interchange X and Y, the order. In other words, I want to find bounds on X that depend on Y and bounds on Y that are independent of X or Z. So that's my goal here. Well, let's start by drawing out this region, this volume. I know Z goes from 1 to 3. And then my X and Y dependency is not affected at all by Z. So let me just come over here and look at these off to the side. So X goes between 0 and this number square root of pi over 2. And Y goes between, use a different color here, between Y equals X and Y equals root pi over 2. So I see on my y-axis, I have a number root pi over 2. And I have a line y equals x coming out from the origin. This is the projection of this solid, this volume of integration, down onto the xy plane. And maybe I'll change these to kind of dashed lines just to indicate that the solid doesn't actually start at z equals 0 down here on the xy plane, but it starts a little bit above. So I make another one of these triangles at z equals 1, just going up 1 unit in the z direction. I make another one at z equals 3. So this little like prism kind of thing, I guess, is my volume of integration here. And those sides are all nice and vertical. You know, my artistic skills are not up to the challenge here apparently, but those sides are all nice and vertical, nice and parallel to the z-axis. Okay, so I see that my setup here is y going from x to pi over 2, so taking, in this sense, like vertical slices from this perspective over here, and then adding up horizontally along x. I want to change my order of integration. Nicely enough, z doesn't come into play. So nicely enough, we can kind of just think of this as though we were changing the order of integration in a double integral, because we're really only focusing on 2 of the variables here, because again, z is just copying everything from z equals 1 to z equals 3. It's kind of independent of x and y, letting us really just focus on these 2 variables. So now what am I going to do? I'm first going along x. I'm first looking at horizontal cross sections, or x goes from x equals 0 to x equals y. And yay, I think that y is going to come in and save the day here, helping us with this integrand. And then I have to accumulate those cross-sectional bits from y equals 0 to y equals root pi over 2. And then, of course, z, well, z just stays the same. We didn't do anything with changing the order of z or anything like that. All right, let's put z on the outside. Z goes from 1 to 3. And here, x depends on y. Y does not depend on x or z, so we need x, the x integral, to be inside of the y integral, so the y integral has to go next. And then x we'll put on the inside. Now, one thing that I might notice is if I think of this as an iterated integral, these inner two, that's basically just a double integral, right? It's actually just the double integral over this region of this function sine of y squared. I can think of it as just a double integral. I note that there are no z's at all in this double integral. There's no z's in the bounds or in the integrand. So it's actually just a number. This whole thing just turns out to be some real number. It doesn't have any z's left in it. So it can actually all come outside of my z integral, leaving me with just the stuff in red times the integral z equals 1 to 3 dz, but that is just 2, right? So this is 2 integral y equals 0 to root pi over 2. Again, we notice that symmetry here, that nothing, that our region of integration doesn't look differently. The cross sections don't look different as I increment along z. So I leveraged that intuition from the geometric side. I saw it in the algebraic side as well. Checked with my integrand, no problem there. Use the symmetry to simplify things. Now I want to integrate x equals 0 to y of sine of y squared dx, but sine of y squared is just a constant. You can either think of it coming out of this integral, or you can think of just getting constant times x evaluated from x equals 0 to y. But integral x equals 0 to y dx is just y. We still have a dy. We got rid of our dz. We took care of the z integral in this 2 out here. And right, I can see that my substitution is now going to work very nicely. So this is going to give me sine of y squared. If I differentiate this, I get, or oops, jump the gun there. Integrating sine gives me negative cos of y squared. If I differentiate this, negative cos differentiates the sine of y squared. Chain rule pops out of 2y, which I have both the 2 and the y here, so that's nice. So I get negative cos of y squared from y equals 0 to root pi over 2. So this is negative 1 times cos of root pi over 2 squared is pi over 2. And then minus cos of 0. Cos of 0 is 1. Cos of pi over 2 is 0. So this all just gives us 1 at the end. Any questions on this so far? Okay, so the next two examples, example 3 and example 4, here we're just looking to set up bounds of integration. So we're not going to go through, a whole integral like this. I think we can kind of see that quite often setting up the bounds of integration is, maybe as much as 80 or 90% of the challenge of the problem. At this point, performing the integrals is usually not a super challenging thing. Both because, after you've gone through Calc 2, you've had a lot of practice at it, and because typically, just practically speaking, when you see a Calc 3 problem, the focus is more on the Calc 3 material and not giving you some crazy integral that you need to use partial fractions or something to complete. So let's look at setting up the bounds of integration for a couple different domains. So here we have a domain That's the region bounded below by this paraboloid. And above by this sphere. So again, let me first draw out the region of integration, the domain of integration. Okay, so what does the paraboloid look like? Maybe I'll make the paraboloid red. Z equals x squared plus y squared. So when x is 0, when we're on the yz plane, it looks like z equals y squared, a parabola opening up. And same on the other plane, so it looks like this. And like that. The perspective's a little wonky here, but I think you kind of get the idea. And then we have a sphere. Maybe I'll draw it in green. X squared plus y squared plus z squared equals 6. Sphere centered at the origin. So of course, qualitatively speaking, this little chunk of a sphere kind of looks a bit like a paraboloid, but it's a sphere, so slightly different shape, but the look is pretty similar. And I see that there is an intersection along what looks like this circular area here. Okay, so I can, well, the first thing I notice is that I can kind of slice along Z first. I see that Z is between, well, between the paraboloid on the bottom part and on the upper part. Well, I have Z equals root 6 minus x squared minus y squared for the top half of the sphere. So those are my bounds on Z that depend on both x and y. So Z in this setup is going to have to be the innermost integral. And then x and y will come outside of there. Now to figure out the x and y bounds, let me pull out the xy plane here. And I see that the projection of this kind of circle of intersection or whatever you want to call it here onto the xy plane is going to be a circle as well. I think that's just kind of intuitive, but we can see that, well, on one hand, z is x squared plus y squared. And on the other hand, z is root 6 minus x squared minus y squared. When are those equal? Well, this is when x squared plus y squared squared equals 6 minus x squared minus y squared. And I guess I could go and kind of multiply all of this out, but I would much rather think in terms of radial distance. I know that thinking in terms of polar coordinates is probably going to be the way to go here. I mean, we obviously have not gotten to cylindrical or spherical yet, but if I just call x squared plus y squared, say r squared, I see that I have r squared squared plus r squared minus 6 equals 0. Or I have r squared plus 3, r squared minus 2 equals 0. Of course, r squared plus 3 equals 0 gives me r squared is negative 3. I can't have x squared plus y squared equal negative 3, at least not in the reals. So I have to have this representing my solution, r squared equals 2, or x squared plus y squared equals 2. I didn't officially change into polar coordinates or anything, but I just recognized that this seems like a polar coordinate type problem. So I'm looking for making a substitution for x squared plus y squared as something else. And I note that I have x squared plus y squared equals 2, which is the circle with radius root 2, centered at the origin. So z goes between this this lower bound and this upper bound. And then we can say maybe y goes between, well, root 2 minus x squared with a plus or minus. So y goes between minus root 2 minus x squared and plus root 2 minus x squared. And we see that x goes between minus root 2 and plus root 2. And when we set up the integrals, we'll have to integrate in this order. Z as the innermost because it depends on both x and y next because it depends on x, and then x is the outermost because it doesn't depend on either. If I had wanted to set up my circle differently, if I had wanted to set it up as x equals plus or minus root 2 minus y squared, and then y goes between minus root 2 and plus root 2, I could have done that as well. So if the integrand rewarded doing it one way or the other, I might have made a slightly different choice here. But since we don't know what the integrand is, this is how we would set it up, either like this or with the roles of x and y switched. Any questions on this one? Okay, so moving on to example 4. So again, just setting up bounds of integration. Here we have a region in the first octant, so when x, y, and z are all positive, bounded above by z equals 1 minus y squared, and lying between the vertical planes, x plus y equals 1 and x plus y equals 3. So again, let's draw a picture of this. Drawing the picture is probably half of the battle. And then kind of deciding how best to slice things up is most of the rest of it. Okay, so z equals 1 minus y squared. I see that that's independent of x. As I vary x, that doesn't change anything about that. So I'm going to get whatever the projection onto the yz axis is just going to get kind of copied along x. So if x is 0, I'm in the yz plane, z equals 1 minus y squared. I'm only worried about the first octant. So in the YZ plane, I'm just going to stick to the top right quadrant in the YZ plane. Well, that's just going from z equals 1, a parabola coming down to y equals 1, z equals 0. And then I have kind of a copy of this coming out along the x-axis. So I have kind of a flat side on the xz plane, a flat side on the xy plane, and then this curved side coming down from this perspective, kind of the top left to the bottom right. So that is this bit. We're also lying between two vertical planes. So these vertical planes are going to cut this. Right now, it's kind of like an infinitely long tube. It could also go in the negative x direction quite a ways as well. It goes in the positive x direction or the negative x direction all the way out to infinity. We're just drawing a segment of it here. So where else are we bounding it? We're going to cut it between two vertical planes. It's going to kind of, if you think of this as like a sausage roll or something, we're taking a slice out of it, both on one side and on the other side. So x plus y equals 1 and x plus y equals 3. I notice that they don't depend on z. So let me just focus. Let me just focus on the xy plane. And x plus y equals 1. Well, when x is 0, y is 1, x is 1, y is 0. That's x plus y equals 1. And then, of course, x plus y equals 3. A parallel line, just a couple units up and to the right. So x plus y equals 1 goes through x equals 0, y equals 1, and comes down here to x equals 1, y equals 0. So that kind of little green two-dimensional structure there that kind of looks a little bit like a cross section of the little thing that's going along the x-axis, but it's angled a little bit, angled at 45 degrees. That's the boundary in the negative x direction. And then x plus y equals 3. So coming out here to say x equals 3, let me draw it in red, keep the color scheme the same. This is parallel to that one. This would come over here and intersect y at 3. It's not going to actually go all the way over there. But again, it kind of comes down and intersects like that. Let me do a little bit of work with my eraser here. So these kind of blue bits at the end here are only for illustration. So I'll draw them as dotted curves now. So really the green and the red kind of segments of planes are the positive and negative x cutoffs. And then the y and z cutoffs are the xz plane, the xy plane, and that curve, or that surface that's kind of coming down here. Okay, so what do we have then? Well, we have, I think z is easiest to set up first. Z pretty clearly goes between 0 and 1 minus y squared. Well, y goes between so I would like to do, I think, y going between 0 and 1. That seems pretty clean over here. Note that this surface, when it comes down, it doesn't allow us to kind of access, in some manner of speaking, this whole region over here. We're kind of cutting this off here. So I've kind of run out of colors, I suppose, but if you think of this green segment as being there, this red segment, line segment as being there, this blue line segment is this there. So hopefully that kind of orients everything for you. So this is really our region of integration in the xy plane. So y going between 0 and 1 is kind of nice. X then is going to go, right, if I integrate this way, that gives me green to red. If I try to integrate dy first, then like sometimes the green curve is going to be the bottom and the blue is the top. Sometimes the x-axis is the bottom and the blue is the top. Sometimes the x-axis is the bottom and the red is the top. That's going to be annoying to do it that way. So if I integrate along x first, x goes from the green to the red. So x goes from 1 minus y, the green, up to the red, 3 minus y. And now y just goes from 0 to 1. So I think z and y were pretty easy to do here, but x was challenging, and particularly once we had to look at the x and y region, figuring out which way to go. It makes a lot more sense for this domain to integrate in this order. So y is going to have to be on the outside. And then x and z, I suppose, could be basically anyway on the inside. As long as both the x and z integrals are inside the y integral, because both of their bounds depend on y. And again, would I switch the order of x and z depending on the integrand? Possibly. It would have to be a pretty darn nasty integrand to switch the order of the y to try to put the y inside, because again, we would probably have to break this into like 3 regions. That's going to be super annoying. So, but this is how we would set this up, either this way or maybe swapping the x and z integrals. But I think the y integral, for all practical purposes, has to be on the outside, unless we had a really heck of a good reason to not do that. Any questions on this one? So again, I think it's, two things just to keep reminding you that when we're drawing these 3D geometric shapes, we're drawing domains of integration. We didn't even talk about, we don't even know what the integrand is. All of this was just for the domain of integration to set up the bounds, and also being able to go back and forth between the algebraic side of things and the geometric side of things, looking at this picture and saying which way dy dx or dx dy is going to work better. Those are two things to remember. Use both the algebra and the geometry. It does take some time to draw out these pictures, but if you draw out the pictures, and particularly if you take some time and draw them out reasonably nice, I mean, I'm no artist, and you can see that, I can draw them fairly decently. I think that is very rewarding. Not rewarding in the I feel contented as a human, but rewarding in the sense that doing a little bit of that upfront work, makes the rest of the problem much easier to do. Okay, questions on anything so far? Okay, let's take a look at example 5 here. This is kind of a typical Calc 3 type problem where the integrand is just very simple, and most of the problem is about setting up the integral and understanding what the region looks like. So evaluate the triple integral of x dv, where our volume of integration is the region bounded above by this thing, z equals 4 minus x squared minus y squared, a paraboloid opening downward, and bounded below by z equals x squared plus 3y squared, paraboloid opening upward that also has kind of an elliptical cross section, where this one has a circular cross section, and we're in the first octet. All right, so maybe I'll stick with a similar color scheme as the one a couple ago. Z equals 4 minus x squared minus y squared. Oh, that's the top one. This is the bottom one. Z equals x squared plus 3y squared. That's a paraboloid opening upward. So it kind of looks like that. And we are in the first octant, so we're only going to draw this bit for positive x and positive y. And then, of course, positive z. And I drew that a little bit tall. Let me actually. I think that's probably a little more accurate. And gives me a little bit of room up here. So then I have z equals 4 minus x squared minus y squared. So I have some paraboloid opening down like this. And it's not easy for me to draw it, but it's not like a nice kind of circular paraboloid on top of a circular paraboloid where the intersection is going to be a nice circle, or kind of the same kind of ellipse for both of them where the intersection is going to be a nice ellipse. It's going to be something that's a little bit difficult for me to draw here. So we do see that integrating dz, we clearly go from the red function on the lower end to the green function on the upper end. So I see z goes from x squared plus 3y squared to 4 minus x squared minus y squared. I don't think there's really a better way to do this, maybe in something like polar coordinates or cylindrical or spherical, but we haven't gotten there yet. So, but I don't think we would want to let y depend on x and z, or x depend on y and z. So z will end up being the innermost integral. And then the question is, what about x and y? Well, again, we kind of have taken care of z at this point. So let's look at x and y separately. If I project this curve of intersection down to the xy axis, or to the xy plane, it's going to give me some curve, right? The curve isn't going to be some kind of crazy curve. It should be something that kind of looks like a circle or an ellipse or something like that, I would think. And now I'm going to lean on the geometry, or sorry, the algebra. I've gotten the geometric understanding. What does the algebra say? Well, I set the z's equal to one another. I can just add x squared and y squared to the other side. And I see I get x squared plus 2y squared equals 2. When x is 0, y has got to be 1. And when y is 0, x has to be root 2. And we do indeed end up with an ellipse out of this. That does not look like an ellipse, but that's maybe a little better. And I suppose just because the y squared has a factor of 2 in it, maybe I'll let x go from minus the plus square root of 2 minus 2y squared. So I'm integrating this direction first. And then I'm going to add up those cross sections. I'm going to integrate over y from 0 to 1. And I don't want to forget that I am integrating x dv here. So I see that z depends on x and y, x depends on y, and y doesn't depend on anything. So y is the outermost integral. X is the next one because it depends on just y. And then z is the innermost. And I'm integrating x, dz, dx, dy. And since this is a lot to write, I think I'm just going to take this out here. I am going to just pull that x outside. It's independent of z. And then, of course, I get top minus bottom right. Integral of dz is just the difference between the bounds. So 4 minus 2x squared, and then what? Plus 2y squared. Dx dy. This gives me integral y equals 0 to 1 of, well, this will give me, I'm just going to do a little bit of scratch work up here. Multiplying will give me 4x minus 2x cubed plus 2y squared x. And then integrating this gives me 2x squared minus 1/2 x to the fourth. Would that be a negative 3y squared? Oh, so in the dz integral,
I think the parentheses are confusing me. I think that's what's going on here.
yeah, so we're integrating from z equals a to b dz. So that's just b minus a, or that's 4 minus x squared minus y squared. The upper bound subtract the lower bound x squared plus 3y squared. So this would be like integral z equals a to b dz, which is just b minus a. So this is like a, and this like b. This is b minus a. And
Okay, so you are subtracting the y squared there then.
yeah,
You're multiplying by -1.
did I get a negative sign off? I think I'm off by a negative sign, aren't I? 4 minus 2x squared. That looks good. But yeah, I forgot to change my sign, didn't I? This distributes into there. Yeah, minus 3y squared minus y squared. That should be a minus 4y squared. All right, yeah, thank you for pointing that out. So, right, negative y squared minus, yeah, negative 4y squared here. Okay, so multiplying through now with that negative 4y squared or minus 4y squared. Now multiplying through. Okay, everything looks good now. And yeah, now if we integrate with respect to x of the green thing, yeah, x squared over 2, that looks good. that looks good. And then minus 2y squared, x squared, x going from minus square root of 2 minus 2y squared to plus square root of 2 minus 2y squared. Okay. Let me double check my notes here. Okay. Yeah, that does look right. I did get that for one of the intermediate steps in the green up here. Ah, I knew that I had made a mistake. Did anybody catch my mistake? I made a silly mistake up here. All the way back when I was setting up the regions of integration. Well, a clue is that I noticed here that I'm integrating an odd function in x over a symmetric interval. Well, this gives me 0, and I knew that when I did it in my notes, I didn't get 0. Something went awry with the bounds on x. What did I do wrong up here in my bounds on x? X actually goes from 0 to positive root 2 minus 2y squared. I just forgot about the bit that it's in the first octant and allowed myself to use the entire top half of the circle. So x actually has the lower bound of 0. So sorry about that. 2 mistakes in 1 problem. This is not my problem, apparently. So x then, in all of these cases, has a lower bound of 0. And now, okay, this is looking reasonable. Whoops, this gets a dy. So 2x squared is 2 times 2 minus 2y squared. Minus 1/2 x to the 4th is 2 minus 2y squared squared. And then minus 2y squared times x squared is 2 minus 2y squared. All of this dy. And I actually notice here, well, if I look at the first and the third terms, I can actually factor out a factor of 2 minus 2y squared. And I'm left with what? 2 minus 2y squared. And then I get minus 1/2 of that same thing. Or that's just one of those things minus 1/2 of them. That's just 1/2. Of that thing. And I'll leave the rest of this for you to clean up because we're down to about 10 minutes left and I would like to get through example 6. But I ended up with 16 over 15 as the answer here. So just multiply out the 1/2 helps simplify a bunch of stuff, and then combine the fractions and you get 16/15. So thank you for correcting my my 3y² mishap there, and just make sure to note that x starts at 0, not at minus √2 minus 2y². So I was focusing a little bit too much on the algebra here and not on the geometry.
Does that happen for every first octant problem or no?
I mean, for, probably for a lot of the ones you're going to see in a class like this, but not necessarily. So I mean, so we could have, let's see, we could have some sphere that is like up here like this or something, that kind of is only on the positive y side of things, but goes say positive y, positive z everywhere, but its x coordinates could be positive or negative. So then like, yeah, then x would start at 0 and go up to whatever. But if we, so here x would look like 0 to whatever. But if we took this sphere and put it on the other side, where here we have x is always positive, z is always positive, but y could be positive or negative, like depending on whether you're on this side or that side of the sphere. Well, now x is going to go from, now x would go from something to something, because we're not actually starting at x equals 0.
Okay, thank you.
Yeah. Yeah, so it is problem dependent, but for a lot of these things that have like a lot of radial symmetry like this, it's going to be kind of a common thing where you see your lower bounds starting at 0. Yeah. Yeah, and I was just being a little bit too reliant on the algebra over here when I did my solution. It was just like, oh, there's my bounds for x, instead of checking back in with the geometry and making sure I got everything just right. Okay, so on to number 6. Here we'd like to find the average temperature in a crystal lying in the first octant, so first octant one again, and bounded by the planes x plus z equals 1 and x plus y plus z equals 3, if the temperature at each point in the crystal is T of xyz equals x. So a lot going on here. Let's first just try to get a graphical representation of this crystal, or this region that's representing the crystal. We're looking at the first octant, so only when x, y, and z are positive. And let's see. I think I'm going to make this one blue. So x plus y plus z equals 3 will make that blue. If x and y are 0, z is 3. And same for the other axes. Whoops. Went a little astray there. So this little kind of chunk of that plane in the first octant is going to represent one of the boundaries of this crystal structure. And then x plus z equals 1. Well, that doesn't care about y. So if y is 0, I'm in the xz plane. X plus z equals 1 goes from 1 to 1. And then we just copy this along the y-axis. Like this. So let me go in here with my eraser and kind of make some of these dashed lines, the ones that don't contribute to being a boundary of the crystal. So I have kind of this boundary over here that's kind of coming into the y-axis at an angle. I have this boundary here. And then, of course, I have my YZ plane, my XY plane, and my XZ plane. So I have something that looks kind of like this if I split it up. Let's see. So we go like this, and I would not really see these. So I would see this face, and I would see a face up here. And so it would kind of go up and then like over. And then that back bit would be kind of a little more rectangular or kind of cuboid in nature for the back bottom part. So it's a little bit, I guess, like a right triangular prism that got kind of sliced at a funny angle. Now, how do I find an average temperature? Well, I want to kind of accumulate all of the temperature to get something like a total temperature, or maybe we would call is like the heat in it. And then I want to divide that by the volume. So I want to integrate temperature over the volume, but wait, the volume is just the integral dV. We'll call this E, this region. So actually, if I go through the trouble of setting up my region and my three integrals and all of that carefully, I can probably use the same work twice here. So I need to find, maybe I'll call it H is the integral of X dV. And then I'll just call it volume is the integral of just one dV. And then I take their ratio. Okay, so I noticed that this angled bit here is going to be the kind of annoying piece to work with. So I probably want to start with that one. I probably want to start by, say, allowing y to go from y equals 0 up to, well, the point that we're interested in for y is on this blue plane, x plus y plus z equals 3, or that's y equals 3 minus z minus x. And then x, well, x is going to go, let me come over here and draw my xz plane. So here at 1 and 1, x can go, say, from 0 to 1, and z can go from oops, drew it the wrong way. So z can go from 0 to 1 minus x, and then x can go from 0 to 1. So z goes from z equals 0 to z equals 1 minus x. And then x goes from 0 to 1, accumulating those cross sections. And the integrals themselves are very straightforward to do. A bit of algebra and so on, a bit of messing with fractions and getting everything right, but you end up with, let's see, h, this integral, the integral of x, is 3/8. V ends up being 7/6, so that's the volume of this crystal. And 3/8 is kind of like the accumulated total temperature, or maybe something along the lines of something like heat in the crystal. And then we take the ratio to get the average of T is, the average temperature is 9/28. So leave the details as an exercise, but the integration is fairly straightforward to carry out. It's just, just a bit of work and just being careful with these bounds, and also don't forget about the X in one of them and make sure to distribute that. Okay, so that finishes up the introduction to triple integrals today. Again, coming back Wednesday, the kind of other two sections that make up the meat of this week, cylindrical and spherical coordinates, we'll knock those both out in one day. And the supplements for this week on surface area, change of variables, a couple of kind of side topics, but also somewhat important. All right, I will see you all on Wednesday. Have a good one.
Oh, I have a question.
Just one sec.